So I hope you remember the one of the big applications of definite integrals is being able to find the area bounded by a curve. And this is exactly what we're asked to do here. We're trying to find the area bounded by f of x and the x and y axes in the second quadrant. And the graph definitely helps us kind of see what it is we're supposed to do. It should be clear that we're starting with x equals -1, ending at x equals 0. So we're going to integrate the area of the area of the shaded region is going to equal the integral from -0 to 1 of f of x dx. So it's just one more application of the antiderivative. So how are we going to take the antiderivative of this beast? Well, it's not actually as bad as it looks, because the exponent, which is a polynomial, is a great thing to let u equal, because when you take the derivative, you get 2x plus 2. And you might say, well, I don't see a 2x plus 2. But you probably notice an x plus 1, and you probably notice that 2x plus 2 and x plus 1 are perhaps somewhat related. So we'll go ahead and factor out that 2 and get an x plus 1. And there's that hiding x plus 1. And then we'll go ahead and solve for dx. So we get 2 over x plus, or du over 2 times x plus 1 equals dx. All right, so that's a good substitution to do. Also note that this is an x value, and this is an x value. So I'm going to make sure that I change my variables as well. If x equals -1, u equals -1 squared plus 2 times -1 equals 1 minus 2 equals -1. And also, if x equals 0, then u equals 0. So in this particular case, oddly, we don't have to worry about changing the bounds of integration. These are now u values. It just so happens that they line up with the original x values. All right, so f of x is x plus 1 times e to the u. Dx is the same thing as du over 2 times x plus 1. So the x plus 1s, which were causing us a little bit of a headache, are gone, so we're good with that. So we have this new integral. We can factor out the 1/2, so let's do that. And the only thing that's left is our familiar e to the u du. And when we integrate that, we get e to the u. We're going to evaluate e to the u. Whoops. We're going to evaluate e to the u at 0 and at -1, and we'll subtract the 2. So we've got 1/2 times e to the 0 minus e to the -1. And, whoa, where'd it go? And that's just going to be 1/2 1 minus 1 over e. Or if you prefer, I kind of prefer this because it's a more compact answer. 1 is e over e, so we can get that common denominator. And we can reduce this all the way down to e minus 1 over 2e. That is your final answer. This is a nice one to check in a calculator. Any decent graphing calculator will be able to do this for you. You can either use the graph and tell it to find the area under the curve, or you can actually just type in the original integral, and you'll get a decimal value. Figure out what that decimal value is compared to the decimal value of our answer, and they should match up perfectly.